Okay, Fred. So here we have another question about isotopes. Now, do you remember what isotopes are?
Oh yeah, isotopes are atoms that have the same number of protons but different number of neutrons.
Very good. Same number of protons, different number of neutrons. An example of an isotope pair would be something like nitrogen uh, 14 and nitrogen 16, right? So which one of these has more neutrons?
Nitrogen 16.
Very good. Nitrogen 16. Which one has more protons?
Nitro protons?
Yeah,
Well, that's the same.
that's right. It's the same. Very good. Same number of protons, different number of neutrons. That's what isotopes are. All right. So we talked about how last time we met, we talked about how you can identify the average mass of an atom, an element, by knowing the natural abundance of the different isotopic masses of the element, right? Well, here we have another question. For example, we're told that there are two isotopes of element Z. First one has 56.5%, and its mass is 152.3 units. If the atomic mass is 155.5, and that means the average, what's the mass of the other isotope? Do you think you know how to answer this one?
Not sure.
Okay, let's push pause, and you guys take a second to read through this and try to figure out, try to get an idea of how to answer it, solve it if you can, and then we'll come back and meet, okay?
Okay.
All right, hopefully you took a chance. You really have to exercise your muscles and to get an understanding of what's going on here. But for this one, we know that there's only two masses, two isotopes, two different kinds, and so 100 minus the 56.5 tells us that the other isotope has an abundance of 43.5%. So I have one that's 56.5% and one that's 43.5%. Okay, and that's for every 100. 56.5 of them are going to have a mass of 152.3. So if I multiply that percentage by its mass, 152.3, and add it to this percentage by its mass, well, in this case, I don't know its mass, right? But I am told the average mass is the 155.5. To get that average, I need to take these sums or the sum of these two products and divide it by how many atoms were counted. And here we had 43.5, and here we had 56.5, and it's percentage, so it's out of 100. So I divide by 100, and so by solving this for x, I can find that it's 159.7. Now, hopefully you can see that you have to multiply these together. This value, we have to multiply by 100, and then we subtract this value here, and then divide by the 43.5. That's algebra. Hopefully you guys can remember how to do the algebra. Okay, good. So here's a question. An element has an atomic mass of 15.987. What mass, or the mass of one of the isotopes is 15 and the other one is 16. What does this mean about the natural abundance of the isotopes? Okay, any idea here, Fred?
I think I got an idea.
All right. Let me ask you this really quick. If we had two isotopes, one that was 15 and one that was 16, and the average atomic mass was 15.5, what would that tell us about the natural abundance of the two isotopes?
I'm not sure. What do you mean?
Well, again, if I had one batch of atoms that had masses of 15 each, and another batch here that had a mass of 16 each, and I count through these atoms, I count through how many there are, right? And I find out that the average is 15.5, which is right in the middle. What would that tell me about how many 15s and how many 16s I had?
Well, I guess that would mean that you had exactly the same.
That's right, because the average ended up being right in the middle. So by looking at what the average is, this case here, it's closer to what, 15 or 16?
15.987?
Yeah,
Closer to 16.
very good. Because it's closer to 16, it means that I know that there's more of isotope Y than there is of isotope X. So that is that the abundance of X is less than that of the abundance of Y. See how we did that?
I think so.
All right. Here's another one. Well, let's see. Let's talk about this first. This number, again, is our number of protons, whereas this number, what did we say this number is?
That's the average mass.
That's right, the average mass. Let's move on now to using what we've learned to answer questions associated with combinations of different elements. So, for example, if we have a certain element X forming a compound with oxygen, in which there's 2 atoms of X for every 3 atoms of oxygen. In this compound, 1.125 grams of X are combined with 1 gram of oxygen. We can use the average atomic mass of oxygen to calculate the average atomic mass of X. All right? And then after we know the calculated atomic mass of X, we can identify what element it actually is. Okay? So this is another way that we can use the atomic mass numbers that are on the periodic table. So, how would you approach this one?
I have no idea. I don't think I understand what's going on here at all.
Okay. So, what do we know about how X and O combine here? X, some element X and oxygen. How do they combine?
In a 3-to-1 ratio?
Oh, or 2-to-1, right?
2-to-1. Oh, yes. Yeah, sorry.
That's right. 2 atoms of X for every 3, oh, not 2-to-1, 2-to-3.
Oh, yeah, 2-to-3.
For every 3 atoms of oxygen. So the chemical formula is X2O3. Is that fair to say?
Yeah, that makes sense.
Okay, X2O3. And then it says that the compound has 1.125 grams of X for every 1 gram of oxygen. So if I said the grams of X over the grams of oxygen, it's 1.125 grams of X for every 1 gram of oxygen. Is that fair?
Yeah.
That ratio there should also be the same ratio for the atomic mass of oxygen, right? And the atomic mass of whatever X is. If we look closely here, we see the atomic mass of oxygen is 15.9994. So this ratio, 15.9994 grams of oxygen, should have a relationship to the grams of X, the grams of X. I don't know what these are, what this mass of X is, but this ratio should be the same because the mass of oxygen in this compound is 1 compared to 1.125 of X, and the mass of oxygen in this compound will also be the mass of oxygens relative to the mass of the X here. Now I do have to put 3 because I have 3 oxygens, and I have to put 2 here because there's going to be 2 X's. Okay, but I can solve for this unknown right here. The way that I would do that with the math, 1.125 over 1 equals 2x over 3 times the 15.9994, or 16. All right, so I'll put that into my calculator here. 1.25 times 3 times 16, so 1.125. Doing cross multiplication times 3 times the 15.9994. And I set that equal to 1 times 2x, which is just 2x. So if I just take that number divided by 2, that's my 26.99. So that is my X, and that must have been the mass of my unknown element. So which element on here has a mass of that? Is it aluminum? Let's see. Aluminum has a mass of, oh, that has a mass of 26.98. How about argon?
No, that's 30 something.
Yeah, that's too high. 38. Silver, Ag.
That's 107.
Yeah, that's a high number there. And gold, Au.
197.
Yeah, 197. So the answer must be aluminum. Okay, did you guys see that, how we did that? So we used the atomic mass of our oxygen to know that the mass of oxygen would relate directly to the mass of the unknown element in this case. Okay, so let's set that up again for ourselves just as a review. 1.125 grams of X over 1 gram of oxygen. Set that equal to 2 unknown amounts of X, grams of X, over 3 of the 16 grams of oxygen. All right, and the math, 1.125 times 3 times 16, cross multiplying those together, setting it equal to these, 2, I'll call that X, times the 1. All right, so 2X is equal to, let me do 1.125 times 3 times 16, 53.99. Divide by 2, X equals 27 or 26.999. Okay, good.